Hello everyone, welcome to MindMatrix Learning. Good evening all of you. Am I properly audible and visible to all of you? Please let me know once. Just confirm once in the chat box so that I can get to know that whether I'm properly audible and visible or not. Hi Abhyuday, good evening, welcome. Okay, thank you. Good evening Abbas. Welcome all of you. Surrounding noise is there. Uh, yes, like I I cannot avoid it. I think it's not loud. Just let me know. If it is too loud, then we can, maybe postpone this session. Just let me know once. If it is too loud, then I don't think it will be, a good experience for you too. Okay, it's fine. Okay. Okay, so let's get started then. Yeah. So we will be solving the questions based on normalization. Most of the previous year questions I will be solving in this class. Okay. So let's get started without waiting anymore. So this is the first question that you have on your screen. I hope it is visible to all of you. So this is from GATE CSE 2001, and yeah, this is based on finding the decomposition, whether it is lossless or lossy, and whether it is preserving the dependency or not. So now we need to solve this question. So let's read this question first. Consider a schema R having these four attributes A, B, C, D, and functional dependencies are given to us. These are the functional dependencies given to us. A determines B and C determines D. Okay, so these are the functional dependency set given to us. Now then the decomposition of R. So what they have done is, so we have this relation R having these four attributes A, B, C, D, right? And they have decomposed this relation, this main relation into two relations, that is R1 and R2. So this R1 is your A comma B and this R2 is your C comma D. Now we need to find out whether this decomposition is lossless or lossy. So what do you think? Is this decomposition lossless or lossy? How do we find that whether a decomposition is lossless or lossy? So this is a binary decomposition, right? As you can see, why I'm saying this is a binary decomposition, because they have decomposed this original relation R into two relations. So this is your binary decomposition. This is binary decomposition, right? If we decompose the relation into more than two relations, then we call it as non-binary decomposition. But in this question they have asked binary decomposition. So for binary decomposition we can directly find out how. We can see whether there is any common attribute is there or not. Do we have any common attribute here? If I do R1 intersection R2, do we have any common attribute here? No, there is no common attribute. Here we have AB, here we have CD. So the intersection is phi. If there is no common attribute, and that common attribute should be a key in one of the relation, then only we can say decomposition is lossless. So here in this case, if you see the intersection is phi, there is nothing common between these two relations, decomposed relations, right? So can I say, what can we say? Is it lossy or lossless? This is lossy, right? Because there is no common attribute here. So this is a lossy decomposition. Is this clear to all of you so far? Do you have any doubt? This is a lossy decomposition, or you can say not a lossless join. Is this clear? Lossy decomposition, or you can say not lossless. Fine. What about dependency preserving? is dependency preserved here? Tell me. So if you see carefully here, we have this AB here. So if I find A, the closure of A, what do I get? I will be getting A. Then using this, I can get B also. So I can say A determines B. Yes, it is preserved in this relation. And similarly, we can say C determines D. It is preserved in this relation R2 also. So I can say both the dependencies are preserved by these two relations R1 and R2. So I can say yes, dependency is preserved. Dependency is preserved. Is this clear? So it is dependent, this decomposition is dependency preserving but not lossless join. So the option C will be the correct answer here, dependency preserving but not lossless join, because it is a lossy decomposition as there is no common attribute, and that common attribute should be a key. So there is no common attribute, that means clearly you can say it is a lossy decomposition. Yes, option C is the correct answer for this question. Do you have any doubt, anyone? If you have any doubt, please let me know in the chat box. Side by side, I'm checking your comments also. Okay, shall we proceed now? Let's proceed to the next question now. This is from GATE IT 2008. So let's see this question. Let relation R having these four attributes be a relational schema with the following functional dependencies. So these are the functional dependencies given to us. Fine. Now there's decomposition of R into this. So they have decomposed this relation, main relation R, into multiple relations here, and we can call them as, let's say R1 is your A comma B, right? R2 is your B comma C, and R3 is your B comma D. So these are the three relations that they have decomposed R into. Right, now again we need to find whether this decomposition is lossless or dependency preserving or not. So how we can check that? So here if you carefully see, here they have decomposed this relation R into multiple relations and more than two relations. So at least three relations are there. So I can say this type of decomposition, now this type of decomposition is non-binary decomposition. Yes or no? This type of decomposition is non-binary decomposition. Is this clear so far? This is your non-binary decomposition. So in case of non-binary decomposition, we can use the tabular method. We can use the tabular method to find out whether it is a lossy or lossless join also, right? Because that is a better approach. Why I'm saying tabular method or matrix method? So why I'm saying so, in case of non-binary decomposition, because if you are using the successive addition of relations, that method, if it says it is lossless, then it is fine, then it will be lossless. But sometimes if it says lossy, then it may be lossless also. That is why we avoid that type of method. We avoid successive, combining the relations. That method we avoid in case of non-binary decomposition. So we use tabular method, which you can also use in case of binary decomposition as well. But binary decomposition is very straightforward, so we don't use tabular, but you can use, okay? But in case of non-binary decomposition, so let's use that. So this is a tabular method that we are going to use, or matrix method, or there are multiple names, right? So basically we are testing for non-binary decomposition. So now how do we use this tabular method? So what we do, it is very straightforward. So see, you have original relation and having these four attributes A, B, C and D. These are the four attributes that you have, right? So what we are going to do is we are going to have the columns with name of the attributes. So we have four attributes, so four columns will be there. Four columns will be there. And as we are decomposing this main relation into three relations, R1, R2, R3, so that will be your rows. So I can say this is your R1, this is R2, and this is R3. Clear so far? So this is R1 is having your A comma B, R2 is having your B comma C, and R3 is your B comma D. Is this clear so far? This is the tabular method, right? So what we do, so let's write the dependencies. What are the dependencies here? We have the first dependency. So we can start with this. So wherever, carefully see this, carefully try to understand this method. It is very simple. In relation R1, we have two attributes A and B. So what you simply do is, you can write A in those two attributes. Similarly for R2, so this is the first step that we do. The second, so in this relation R2 we have these two attributes B and C. So what you do, so you simply write AA, or you fill the entry with A in those attributes. Similarly for R3 it is B comma D, so you will be writing A here and A here in column B and D respectively. Clear? This is the first step. Now what is the next step? What is the next step now? The next step is also very, very simple. Carefully understand this. In the next step, so let me just write all the dependencies here so that we can refer it easily. A determines B. This is the functional dependency given. B determines C. C determines D and D determines B. So this is the functional dependency set given to us. Now what we do? The first step, it is clear. I hope it is clear that we first fill the entries A based on the attributes that we have in each of the relation. Now the next step is, let's consider one by one every functional dependency. Here it is A determines B. So now we need to see here A determines B. That means here if you see A determines A, that is fine. Now do we have anywhere else in any other row, do we have like this? So here if you see there is blank entry. So nothing we can do here. What about this one? There is a blank entry, nothing we can do here. Okay. What about B determines C? B determines C, A here and C, we don't have anything, right? But here if you see A determines C, so A here. Similarly, wherever now you are going to have A, corresponding to it in the column C, you will be filling A also. Because here it is, once we know that B determines C and here it is A, so here also we are going to add A here. Similarly, here also we will be adding A. Is this step clear so far? Do you have any doubt? Anyone? Because B determines C is there, so we know that B determines C, A determining A. So here also I'm going to fill, by taking the reference of this, here also I'm going to fill the same thing as A determines A. Then what else we have? C determines D. C determines D. Here it is nothing, here it is nothing. But if you see here, A determines A, C determines D, so A determines A. So here also I'm going to add A here, because it is C determines D. Right? Now when to stop? Like you can consider now the next functional dependency also. But when to stop? You can stop when the entire row is filled with A entries. If the entire row is filled with A entries, then you can clearly say that it is a lossless decomposition. It is lossless decomposition. Then you can clearly say if the entire row is filled with A. Or you can keep continuing it. Let's say D determines B. So D determines B means A. So this is done. Now even if you check for other functional dependencies again, still there will be, if there is no change, then you can also stop. So there are two ways when you have to, there are two things you have to consider when to stop. The first, if the entire row is, if any one of the row is filled with A's completely, then you can stop and you can clearly say it is a lossless decomposition. Let's assume in some example, let's say if it is not filled, the entire row, any one of the row is not filled with A's, then in that case you will keep on repeating these functional dependencies, and if you find there is no change at all, then what you can do, then also you can stop, and then you can say it is a lossy decomposition. So we will be solving one or two more questions here in the previous year like this. Okay, so you will gain more understanding once we proceed. Is this point clear to all of you? So this is a lossless decomposition. Why? Because the entire row is filled with A. Do you have any doubt so far? So I'm not explaining the entire, like I'm not writing the steps here, but yes, this is the procedure, and in the lectures we cover these steps, right? But here, as we are just solving the previous year questions, so I'm giving you the overview, the brief overview, or you can say the brief idea how we are going to solve it. So this is a lossless decomposition. We can clearly say this. Is this clear to all of you? But what about dependency preserving? What about dependency preserving? Is dependency preserved here? So here, if you see, if I consider this relation, if I find A closure, what do I get? I will be getting A, and then A can determine B, so I'm getting B here. So A determines B, definitely it is there. What else? So this dependency is preserved. What about this one? If I find B closure, what do I get using this functional dependency set? I'm getting B, I'm getting C, I'm getting D, right? So, but I'm not getting A. So can I say just this is the one functional dependency that we are getting from this one? What about this one? As you find the B closure, you are getting B determines C. So this is preserved. This is preserved. Now if I find C closure, C can determine D also, D can determine B also. So can I say C determines B will also be there? Fine. That this functional dependency will also be there in this relation. What about R3 relation? B determines D is there. Why? Because B can determine D. What about a D? So let's find the D closure. You are getting D here. D can determine B, right? And B can determine C. So basically D can determine B, right? D can determine B. We can clearly say because D determining B also. Now, so I can say A determines B. This is preserved. B determines C. This is preserved. D determines B. This is also preserved. What about this one? Tell me about C determines D. What about this one? Is this preserved or not? That is the question now. Is it preserved? Now what we do? We consider all the functional dependencies together and then we try to find out whether C determines D is preserved or not. So if I find a C closure, let's consider all the functional dependencies. All the functional dependencies we can consider. Right? Then check. Then find the closure. So C can determine B. Yes. C can determine B. B can determine D also. So can I say C determines D as well? Can I say C determines D as well? This is how we check for functional dependency preserving. Functional dependency preserving. This is the way how we can check. So what we do, we simply say, let's say if we have relation R1, R2, R3, corresponding to it, I will be having F1 functional dependency set, F2 functional dependency set. If I take the union and the closure of that, if it is equal to closure of F, closure of the original functional dependency set, then I can say dependency preserved. Then I can say dependency preserved. Is this clear to all of you? Do you have any doubt? Just let me know in the comment section, in the chat section. Let me know if you have any kind of doubt here. Yes, Abhyuday, Abhas, everyone. Is this clear or do you have any doubt? Clear? Right? Okay, good. So we can say dependency is preserved and it is lossless join. So option, yes, option A is the correct answer here. Given a lossless join and it is dependency preserving. I hope it is clear. Let's proceed to the next question now. And this question is from GATE CSE 2021 set 1 question. So here also we need to find out whether, here just we need to check whether it is a lossless or lossy decomposition. There are two decompositions given here, D1 and D2, and this is the functional dependency set given to you. Right? And you can see both the decompositions are non-binary decompositions. Both the decompositions are non-binary decompositions. Clear? So here let's try to check whether it is lossy or lossless. So this is the functional dependency set given to us and this is the first decomposition. So again what we can do? Again we can use the tabular method. So here how many attributes we have? So all these are the attributes that we are having. So what we can do is P, Q, R. Okay, R is not there. So P, Q, S, T, X, Y, Z, W. These are the attributes that we have, right? These are the attributes that we have. And how many relations? R1, R2, R3, R4. So let's say this is your R1, this is R2, this is R3, this is R4. Fine. So this is your PQST, this is your PTX, this is your QY, and this is your YZW. Now the same thing we have to do as we did in the previous question. So here if you see PQST, so wherever we have these attributes, just mention A over that. Just fill the entries of A in those columns. Similarly here PTX, so PTX, QY here, so QY here, right? Fine. And here YZW, so YZW. Clear so far? Any doubt, anyone? So this is the first step that we follow in this tabular method. This is the first step. Now what else we need to do? Now based on this functional dependency set, as you can see here, the first is PQ determines X. So PQ determines X. So AA, let's say it determines what? Do we have any other entries? No. So PQ determines X. Let's fill this with B. Let's say I'm filling it with B, maybe. Like as we are not sure as of now, so we can fill it with B or any other, character. Right? So PQ determines X. Here we have nothing. Here we have nothing in P. Here we have nothing in Q. That's it. Okay. Then P determines YX. P determines YX. Is this clear so far? P determines YX. So A determines YX. Now what to do now? what we need to do here? So similarly, P determines YX. So similarly here also we can fill. Yes or no? Are you getting this or not? Here also we can fill. Right? So if you see here, P determines YX. So let's say it is B only. So A determines BB. I'm talking about this functional dependency. P determines YX. So here it is A. Let's say here it is B. And let's say here also it is B. Then again, if you see here, here also P determines YX. So A determines A. So here also what we can do? We can write B here. Yes or no? We can write B here. Based on this value, A determines this. So here also I can write. Here it is A, here it is B. I hope you are getting this. Anywhere else, value P is not there, so nothing to do here. Similarly, we have Q determines Y. Q determines Y. So A determines B. A determines A. So if A determines A, I can say that here B should be A only. I can also say that here B should be A only, because A determines A here. So this also become A. That's it. Here we don't have the value of Q. Here we don't have the value of Q. So nothing to do here. Okay. Then Y determines ZW. Y determines ZW. So if you see carefully, Y determines ZW. So A determines, let's say, maybe we can fill the value, let's say BB. Y determines ZW. But if you see here, A determines AA. So I can say that here also it should be AA only, right? Here also should be AA only. Is this clear so far? Do you have any doubt? Now we can repeat. Again. So PQ determines X. So PQ determines X. So here it is B only, right? Okay, that is fine. Now carefully say this. P determines YX. So we have to repeat it for every functional dependency. P determines YX. So A determines YX. So here it is AB. So what we can do? Here it is BA. So can I say here also it should be A? Here also it should be A. Yes or no? Are you getting this point or not? Because here if it is A determines A and some B is there. So here also A determines it should be A only, right? Because if it is A, here also it should be A. Right? So now if you carefully observe, the entire row is filled with A only. The entire row is filled with A only. So we can say it is a lossless join. It is a lossless join. Is this clear? Do you have any doubt? So D1 is your lossless join. D1 is your lossless join. I hope it is clear. Let's check for D2 now. Similar way. Here it is P, Q, S, T, X, Y, Z, W. the same way we have to follow. So let's say it is R1 here, R2 here, R3 here, R4 here. So here we have four relations. So R1 is your PQS, R2 is your TX, this is your QY, this is your YZW. Fine. Now carefully see this. So what we need to do, we need to fill, the first step is wherever we have these attributes, just fill A here. So A, PQS, TX, so A, QY, so A, and YZW, so A. Fine so far. Now what is the next step? Now consider the functional dependency here. PQ determines X. PQ determines X. So do we have any other entry of PQ here? No. PQ here? No. PQ here? No. So I can assume, let's say it is B. Let me use another color just to differentiate. Let's say I'm assuming, let's say it is B. Let's say it is B. Then P determines YX. P determines YX. So P value is not here, P value is not here, P value is not here. So P determines YX or XY, you can say simply. So here I can say it is B. Let's say it is also B here. Fine so far. Q determines Y. Q determines Y. Here it is A determines A. Here it is A determines B. So can I say here also it should be A only? Because if it is A determines A, here also it should be A only. So I have replaced B with A. Clear? Let's proceed. Y determines ZW. Y determines ZW. Here A determines AA. So here also A determines AA. Here also A determines AA. Is this clear? Now, so far, if you carefully observe, no row is filled entirely with A, right? So what to do? Again repeat, again check. From the first functional dependency, again check and then see whether there is any change or not, further any change or not. PQ determines X. So PQ determines X, fine, no change because PQ value not here, P value not here, PQ value not here. So this will remain as it is. P determines YX. P determines YX. So A determines, so BA it should be, because A value is not here, P value that is not here, right? So it should be as it is. Q determines Y. Q determines Y. A determines A determines A. That's it. Y determines ZW. Y determines ZW. So A determines A determines A determines A. So you can clearly see now there is no change. No change is happening further. Even if you repeat, no change is happening. So there is no row that is filled entirely with A. So we can clearly say that this is a lossy. This is a lossy decomposition. This is a lossy decomposition. Is this clear so far? This is a lossy decomposition, right? So D1 is lossless, but D2 is lossy decomposition. Option A is the correct answer here. Do you have any doubt, anyone? Yes, Abhas and Abhyuday, is this clear? If you have any doubt, please let me know. Right? Any doubt so far? Are you able to follow or not this method of tabular method or matrix method to check whether decomposition is lossless or not? If you have any doubt, you can definitely ask in the chat section. Okay, fine. So let's proceed with this next question, GATE CSE 2019. So let's see here. Let's read the question now. Let the set of functional dependencies, this is a functional dependency set given to us, hold on relation schema X having these attributes PQRS. X is not in BCNF. It is already given to you that X is not in BCNF. So you have one relation, let's say X. Suppose X is decomposed into two schemas Y and Z. So X is decomposed into two schemas Y and Z. And this Y is your PR and Z is your QRS, right? and X is your PQRS. Is this clear? So this is given to you. Now consider the two statements given below. Both Y and Z are in BCNF. What do you think? Both Y and Z are in BCNF? How to check whether a decomposition is BCNF or not? So it is very simple. If X determines Y, then this X has to be a super key. In case of BCNF, this X has to be, the LHS has to be a super key. Then only you can say that the decomposition, that this, if it is valid for every functional dependency, then we can say then it is a BCNF decomposition. Yes or no? So if you talk about this Y relation here, let's try to find out P closure. Let's try to find out what are the functional dependencies present in this relation Y. So if you find P closure using this functional dependency set, I will be getting P. Am I getting anything else? No, nothing. Okay. If I find R closure, what do I get? I'm getting R. Then using R, I can get P also, right? Anything else? No, that's it. So I'm getting this thing, right? So I can say R determines P is there. R determines P is there, and can I say R this is my super key because it is able to get all the other attributes of this relation. So can I say that Y is in BCNF? I can clearly say Y is in BCNF. Yes or no? Because this is a super key here. But what about this QRS? What about this QRS? So here also we need to check. So let's see, if I find the closure of Q, what do I get? I'm getting Q. Anything else? No. If I find the closure of S, I'm getting S, and S can determine Q, so I'm getting Q also. Anything else? No. So S determines Q is definitely there. What else? If I try to find the closure of R, I'm getting R. Anything else? P is not there in this relation. That's it. That's it. So, and if I find the QR closure, I'm getting QR, and using QR I can get S also. So I can say yes, I'm getting QR determines S, this functional dependency we are getting. So here for this particular relation, I'm getting QR determines S, I'm getting S determines Q. Yes or no? I'm getting S determines Q, I'm getting QR determines S. Now tell me, is this relation Z, is it in BCNF? Is it in BCNF? If you carefully see this QR, this is a super key here. But is this S a super key? Carefully see this functional dependency. Is this is this S a super key? No, it's not a super key. Why? Because you are not able to get all the attributes of this relation using this if you find the closure of S, right? So due to this one, you can say this is not in BCNF. This is not in BCNF because this is not a super key, right? So here the statement is both Y and Z are in BCNF. No, that is false. That is false. This is not correct. Y is in BCNF, but Z is not in BCNF. Is this clear? Any doubt, anyone? Now let's see the second statement. Decomposition of X into Y and Z is dependency preserving and lossless. So this is a binary decomposition. Two relations are there. So first check for lossless or lossy. So do we have any common attribute? Yes, R is our common attribute. Is R a key in any one of the relation? Yes, it is a key in one of the relation, that is Y here, because R determines P, right? And this is a key here. So I can say, yes, it is lossless. As R is the common attribute in these two relations and it is a key in one of the relation, so we can say this decomposition is lossless decomposition. What about dependency preserving? Dependency preserved or not? Let's see. R determines P. Yes, it is preserved here. S determines Q. Yes, it is preserved here. QR determines S. Yes, it is preserved here. So all the dependencies are preserved. So this is dependency preserving and this is lossless as well. So second statement, it is true. Second statement is correct here. So option, and we have to find which of the above statement is or are correct. Only second is correct. So option C is the correct answer here. Is this clear to all of you? Do you have any doubt? If you have any doubt, please ask. So I'm solving these questions quickly so that it will be a kind of revision, right? I hope you understand. I'm not explaining the entire concept. I'm explaining the concept, but not in lot of detail. So I'm just quickly solving it so that it will be a kind of revision for you. You will be able to recall every concept, and this will be very helpful for you. So option C is the correct answer here. Let's proceed to the next question that we have, which is from GATE CSE 2014 set 1. Okay, so let's solve this. Given the following two statements, so these two statements are given. Statement 1 says every table with two single valued attributes is in 1NF, 2NF, 3NF and BCNF. Is this statement correct or not? If I have, let's say I have a relation R and I have just two attributes, let's say AB. Is this relation in 1NF, 2NF, 3NF and BCNF? Let's talk about 1NF first. Here it is saying single valued attributes. So definitely it is in 1NF, and by default in relational model every relation is in 1NF. So definitely it is in 1NF. But what about 2NF? If I have just two attributes here, can we have partial dependency? Can we have partial dependency if I have only two attributes? Not possible, right? We cannot have a partial dependency. See, either let's say A is going to be my key, or let's say B is going to my key, or AB can be my candidate key, right? So if you see here, if I have just A, then there is no point of having partial dependency. Just B, no partial dependency. What about this one? Here only these two attributes are there. There is no other attribute. There can be no other non-prime attribute if this is my candidate key. Definitely no chance of partial dependency. What kind of partial dependency I'm talking about? If I say 2NF, if I'm talking about 2NF, so this kind of partial dependency, if it is there, let's say some candidate key determining non-prime attribute. If this kind of partial dependency is present, then we can say it is not in 2NF. If this kind of partial dependency is present. When this kind of partial dependency can be present? When some subset of this candidate key determines this non-prime attribute. Yes or no? When subset of this candidate key, some subset of candidate key, proper subset you can say. Let me write in that way. So we can say here proper subset of any candidate key determines non-prime attribute. If this is the violation, if this kind of violation is present, this is a violation of 2NF. If this violation is present, then I can say this kind of partial dependency is there. Then I can say this is my partial dependency, that some candidate key determining non-prime attribute. But if I have just this as the candidate key, there is no other non-prime attribute, so there is no question about having this kind of partial dependency, right? So definitely it will be in 2NF. What about 3NF? So similarly for 3NF also we can say there will be no transitive dependency. If we have for 3NF, let me write this also for 3NF, if some candidate key determines non-prime attribute, transitively dependent. If it is transitively dependent, then we can say that relation is not in 3NF. If this kind of transitive dependency is there, then we can say the relation is not in 3NF, right? But if that is not possible if I have just two attributes here, right? You can consider any case here, any candidate key here. So definitely this is in 3NF as well. And what about a BCNF? What about BCNF? See, either A is a key, B is a key, or AB is a key. If A is a key, that means A determines B. If B is a key, that means B determines A. If AB is the key, that means AB is my super key or candidate key. AB determines AB only. Now, here also this is my super key. So yes, it is in BCNF. This is my super key. So yes, it is in BCNF. This is my super key. Yes, it is in BCNF. So that means if I have just two attributes, that relation will be in BCNF. So in other way also you can say, if it is in BCNF, definitely it will be in 3NF, 2NF, 1NF also, right? So this way also you can answer. So if you check for BCNF, then you can clearly say it is in 1NF, 2NF and 3NF as well, right? So anyway you can answer this. So this is correct statement. This is true here. This is true here. Is this clear? Any doubt, anyone? If you have any doubt, please ask. What about this S2 statement? Here we need to find the minimal cover of the set of following functional dependencies, right? So here it is asking that this functional dependency set is a minimal cover for this one. So how we can check minimal cover? This type of question we have already solved in the previous session as well, right? So we need to find whether this functional dependency set is a minimal cover of this one or not. So if by using this functional dependency set, if I can get all these, then I can definitely say it is a minimal cover. Otherwise no. So let me solve this here. So here let's try to find out this AB determines C. So that is already given. So this is fine. What else? D determines C, that is already given. So no need to do anything here, right? And what about this one? E determines C. So E determines C, that is also there. What about AB determines E? What about AB determines E? Can we get AB determines E using this set? Let's try to find the closure. We are getting A, we are getting AB. Using AB we can get C also, and that's it. We are not getting E. That means this AB determines E we are not getting, right? So can I say this is not a minimal cover? This functional dependency set is not a minimal cover for this functional dependency set. Why? Because AB determines E is the functional dependency that we cannot get from this functional dependency set, as you can see here after finding the closure of AB using this set. So definitely it is false. So first is true, second one is false. So option A is the correct answer here. Is this clear? S1 is true and S2 is false. Do you have any doubt here? Let's proceed to the next question now. This is from GATE CSE 2020. Let's see this question. Let's read this question. Consider a relation table R that is in 3NF. It is already given that relation R is in 3NF but not in BCNF. Now understand this thing. When can we say that a relation R is in 3NF? When something like this is there. Either X is a super key or Y is a prime attribute. Yes or no? Either X is a super key or Y is a prime attribute, then only I can say the relation is in 3NF. And what about BCNF? If we have something like this, X has to be a super key. There is no other choice. X has to be a super key. Then only you can say the relation is in BCNF. Right? Then only you can say the relation is in BCNF. Fine. Now let's try to read which one of the following statement is true here. Let's try to find out. Option A. R has a non-trivial functional dependency X determines A, where X is not a super key and A is a prime attribute. Is this correct? When I say relation R is in 3NF but not in BCNF, so X is not a super key, fine, but A is a prime attribute. Even if A is a prime attribute, that means here Y is a prime attribute, I can say it is in 3NF and I can clearly say it is not in BCNF. Why? Because X is not a super key, it is clearly mentioned. So can I say this statement is true here? Option A is true here, right? What about other options? Option B says R has a non-trivial functional dependency where X is not a super key, okay, and A is a non-prime attribute. If A is a non-prime attribute, then that means what? Then that means it is not even in 3NF. It is not even in 3NF, right? Is this clear? So definitely this is also incorrect. R has a non-trivial functional dependency X determines, say, where X is not a super key and A is a non-prime attribute, right? Again, it is saying A is a non-prime attribute. If X is not a super key, right, and A is a non-prime attribute, that means this is not valid, this is not valid, definitely this is not in 3NF. This is not even in 3NF, right? But here it is given to us that R is in 3NF but not in BCNF. So again, this is also incorrect. A cell in R holds a set instead of an atomic value. So what about this one? A cell in R holds a set instead of an atomic value. If this is the situation, then this relation R is not even in 1NF, because here it is saying it is holding a set instead of atomic value. Then it is not in 1NF also. So again, this is also incorrect based on what is given to us. So option A is the correct answer here, and that is the only true statement that we have here. Is this clear? Any doubt, anyone? So if you have any doubt, you can ask in the chat section. Let's proceed to the next question now. This is from GATE CSC 2013. A relation R has 8 attributes. So these are the attributes that we have. R contains only atomic values, that is fine. Functional dependency set is given to us, right? And we need to find whether this relation is in 1NF, 2NF, 3NF or BCNF. This is what I need to find out. Yes or no? Is this clear? So let's try to solve. How we can solve this? First we need to find out the candidate keys. So I have A, B, C, D, E, F, G, H. These are the attributes in this relation R, right? So let's first try to find out the candidate keys. So how to find the candidate keys? You need to see what we can determine from the functional dependencies. That means you need to find out the attributes which are not present on the right hand side of the functional dependency. If you see A is present, if you see BC is present, what else? CFH is present, EG is present, D is not present. That means D must be part of every candidate key. D must be part of every candidate key. That means, let's say, first I try to find the D closure. So I'm getting just D, nothing else. So that means just D is not a candidate key. So we need to add some more attributes. Let's say we are considering 2 attributes now. AD closure. So I'm getting A, D, what else? Using A, I'm getting BC also. Anything else? Using B, I can get C, F, H also. Right? Using F, I can get EG also. Right? All the attributes we are getting. So yes, AD is my candidate key here. AD is my candidate key here. Okay. What about BD closure? What about BD? I'm getting B, I'm getting D. Anything else? Using B, we can get C, F, H. Right? Anything else? Using F, I can get EG. And using E, I can get A also. So this is also my candidate key. This is also my candidate key. What about CD closure? CD. That's it. This is not my candidate key. What about ED closure? So I'm getting E, I'm getting D. Then using E, if I can get A also. So definitely I can get all the attributes, because using A, I can get all the attributes. So ED is also my candidate key. Okay, what about, what do we have else? FD. FD is my candidate key or not? So I'm getting F, I'm getting D. Using F, I can get EG. So once I get E, I can get A. So that is also my candidate key. Okay, then what about this GD? I'm getting G, I'm getting D. Anything else? No, this is not my candidate key. What about HD? So I'm getting H, I'm getting D. Anything else? No, this is not my candidate key. Now even if you take the combination of CGD, CHD, still you will not get all the attributes. So I can say these 4 are the candidate keys here. If these 4 are the candidate keys here, now carefully say this. Do we have, so it is in 1NF for sure because only atomic values. Now first check for 2NF. Do we have any partial dependency here? Do we have any partial dependency here? Here it is AD. So if you see, we have this kind of functional dependency. So let's first write the non-prime attributes. Let's first write the non-prime attributes. because that is important to check for the partial dependency also, right? And transitive dependency as well. So what are the non-prime attributes? Those attributes which are not part of any candidate key. So here if you see A, B, D, A, B, E, F, D, these are the prime attributes. So that means the remaining G, H, what else? Any other attribute which is not there? F is there, A is there, B is there, C is not there, so C also. So these are the attributes which are non-prime attributes. Now, do we have any partial dependency? This kind of partial dependency. So if you see here, A determines BC. So is this a violation? Understand this thing. Is this a violation? Right? What kind of partial dependency I'm looking for? For 2NF, I'm looking for this kind of partial dependency where some candidate key determines non-prime attribute, right? And that too partially dependent. So partial dependency is there. This kind of partial dependency I'm looking for. So if some subset of a candidate key can determine non-prime attribute, I can say that is my violation. So if you see, C is my non-prime attribute and part of a candidate key, because AD is my candidate key, part of it, proper subset of it determining a non-prime attribute. So this is a violation. This is a violation of 2NF, right? So can I say that AD determines C? This is my partial dependency that is existing here. AD determines C, this is the partial dependency that is existing here because part of it, that is A, determines C also, which is a non-prime attribute. So this relation is not in 2NF. If it is not in 2NF, then there is no point in talking about 3NF and BCNF, because if it is not in 2NF, definitely it is not in 3NF as well as in BCNF. Is this clear to all of you? Do you have any doubt? So this relation is only in 1NF, that's it. So option A is the correct answer here. It is in 1NF but not in 2NF. Okay. Let's proceed to the next question now. GATE CSC 2012. Which of the following is true? So we need to find the true statements here. So carefully say this. Option A is every relation in 3NF is also in BCNF. Try to understand if this relation is 1NF. So we can write like this, or we can make it like this. See, if a relation is in BCNF, right, then definitely it will be in 3NF also. If a relation is present over here, definitely it is in BCNF, 3NF, 2NF and 1NF also, right? So like this we can make a Venn diagram, and this is in 1NF. So what is mentioned over here in this first option A? Every relation in 3NF is also in BCNF. If I have one relation here, definitely it is not in BCNF. So this is false. This is false. What about option B? A relation R is in 3NF if every non-prime attribute of R is fully functionally dependent on every key of R. Here it is talking about 2NF. This is the definition of 2NF. When every non-prime attribute is fully functionally dependent on every key of R, right? Or in other words, you can say no non-prime attribute is partially dependent on any of the key, right? So this is the definition of 2NF, not 3NF. So that is the reason this is also false. What about option C? Every relation BCNF is also in 3NF. Every relation in BCNF is also in 3NF. Yes, this is true. This statement is true. No relation can be in both BCNF and 3NF. No, if I have a relation in BCNF, definitely it is in 3NF also. So this is also false. So option C is the correct answer here. Option C is the correct answer here. Is this clear to all of you? Do you have any doubt? Shall we proceed now to the next question? If you have any doubt, please ask. Okay, let's see this one now from GATE CSC 2007. Which one of the following statement is false here? We need to find the false statement. Okay, let's see this. Option A says any relation with two attribute is in BCNF. We have already seen this in one of the question. If I have only two attributes, definitely it is in BCNF. So this is true. A relation in which every key has only one attribute is in 2NF. Yes, if every key is having only one attribute, there is no chance of getting partial dependency. There will be no proper subset. If I have just one attribute in X, right? If just one attribute is there, then there is no point of having the partial dependency, because there will be no proper subset then, which can determine non-prime attribute. So definitely this is also true. What about option C? A prime attribute can be transitively dependent on a key in a 3NF relation. A prime attribute, what it is saying, in a 3NF relation, a prime attribute can be transitively dependent on a key. So let's say some candidate key is there. Is this allowed in 3NF? What do you think? Is it allowed in 3NF? A prime attribute is transitively dependent on some candidate key. Yes, it is allowed. Yes, it is allowed. Yes or no? Yes, there is no problem. What kind of transitive dependency is a problem for us in 3NF? If I have something like this, some candidate key determining a non-prime attribute, some candidate key determining a non-prime attribute. So this type of transitive dependency is there. This is a problem. This is a problem. For 3NF, this is a problem, right? But if I have prime attribute, then there is no problem. This is also true. Yes, we can have this kind of transitive dependency. What about option D? A prime attribute can be transitively dependent on a key in a BCNF relation. Now this is interesting. Carefully, let's try to understand. Here it is saying in BCNF, a prime attribute can be transitively dependent on a key, right? This is what it is mentioned on some candidate key. If this is the thing that I have, is this possible in BCNF? What do you think? Is it possible in BCNF? See, what is transitive dependency? If I have some X, right, determines, let's say, some attribute, non-prime attribute A. If this kind of transitive dependency is there, how this is transitive dependency? If I have something like this, X determines, let's say, maybe, you can say B or beta, let's say, determines A, and beta can not determine X. If this is the scenario, also A is not your X and A is not your beta. If this is the scenario, then I can say this is my transitive dependency, right? If this kind of situation is there, then only I can say X determines A will be a transitive dependency. Now here what it is saying, some candidate key determines, or you can say some prime attribute transitively dependent on some candidate key. Is it possible in BCNF? Try to understand this thing. Is it possible in BCNF? See, let's say some candidate key is X, right? And some prime attribute may be A. Let's say some prime attribute is A. Now, can we have this kind of transitive dependency? So if I'm saying this kind of transitive dependency is there, what does that mean? That means some beta is there which determining A, and beta cannot determine X. This is what I'm trying to say. But you know this, that means this kind of functional dependency is also present. If beta determines A is there, this type of functional dependency is also present. If this type of functional dependency is present in BCNF relation, this definitely will be a super key. And if this is a super key, then by contradiction, is this possible that B cannot or beta cannot determine X? Not possible, because if this is your super key, definitely it will be able to determine X also. So can I say this is not possible? This type of transitive dependency is not possible when we have a prime attribute. I hope it is clear, right? So that is the reason why this statement is false. A prime attribute can be transitively dependent on a key in a BCNF relation. So by contradiction, we have proved it that it is not possible. This statement is false. So option D is the correct answer. Is this clear to all of you? Do you have any doubt? I hope it is clear. Let's proceed to the next question now. That is from GATE CSU 2005. Which one of the following statements about normal form is false? Again, we need to find a false statement over here. Option A says BCNF is stricter than 3NF. Yes, it is true. Why so? Because in 3NF you have a choice. Either if you have this kind of functional dependency, you have a choice in 3NF. Either this is a super key or this is a prime attribute. But in BCNF, the choice is even not there. X has to be a super key in BCNF. X has to be a super key in BCNF. So that is more stricter than 3NF. Are you getting this or not? So option A is true here. Statement A is true here. Is this clear? Let's talk about the second option. Lossless dependency preserving decomposition into 3NF is always possible. What do you think? Yes, in 3NF, if you are decomposing into 3NF, it will be lossless and dependency preserving also. This is true. But that is not the case in case of BCNF. So if you are doing decomposition to BCNF, lossless, definitely it will be lossless. If you are doing BCNF decomposition, then definitely it will be lossless, but dependency preserving, it may or may not. It may or may not preserve dependency, right? So here it is saying always possible. No, always not possible. Dependency, it may or may not preserved. And what about option D? Any relation with two attribute is in BCNF. That is absolutely true. We have seen the proof also, right? So which one is false? Option C is false over here. Is this clear to all of you? Do you have any doubt? I hope it is clear. Fine. Any doubt, anyone? Just let me know once. Abhyuday and Abhas. Crystal clear? Shall we proceed now? This is from GATE IT 2008. So a relation is given to us, right? And functional dependency set is given to us. And we need to find again, like whether it is in 3NF, 2NF, BCNF, and so on. So in order to find it, first we need to find the candidate keys. So let's find out the candidate keys. So we have all these attributes A, B, C, D, E, P, G. So how to find the candidate key? First, we need to find those attributes which are not present on the right hand side of the functional dependencies. So CD is present, P is present, E is present, G is present, right? That's it. CG, E, P, CG, E, P and D. So AB is not present. That means AB must be part of every candidate key. So let's try to find out AB closure first, whether this is a candidate key or not. So if you find AB closure, you are getting AB. What else? Using AB, you can get CD also. Nice. Using C also, you can get E also. Yes. What else? Using D, you can get P also. Using P, you can get C. C is already there. Using B, you can get G also. So we are getting all. So that means this is the candidate key. This is the candidate key only. Now tell me, is it in 2NF? First check for 2NF. Is it in 2NF? Do we have any kind of partial dependency here? So what are your non-prime attributes? If you write the non-prime attributes, what are the non-prime attributes that we have here? All other attributes other than AB. That means C is there, D is there, E is there, P is there, G is there. All these are your non-prime attributes. Now, do we have any kind of partial dependency here? Do you find any violation of 2NF? So if you carefully observe, yes, if you carefully observe this dependency, B determines a G. So if you see, this is a violation of 2NF. This is a violation of 2NF. Why this is a violation of 2NF? Because proper subset of candidate key. This is your candidate key AB. Proper subset. B is the proper subset of candidate key determining a non-prime attribute. Right? Why this is a violation? The violation is proper subset of candidate key determining a non-prime attribute. Determining a non-prime attribute. This is the violation. Due to this violation, what is my partial dependency here? AB determines G will be my partial dependency here. Yes or no? Because a proper subset of this candidate key determines non-prime attribute. So this is my partial dependency. This is the partial dependency present over here. Is this clear? So that is the reason it is not in 2NF. It is not in 2NF. So option D is the correct answer here. If it is not in 2NF, definitely not in 3NF, not in CNF, BCNF. Is this clear? Any doubt, anyone? Option D is the correct answer for this question. Let's proceed to the next question now. GATE IT 2005. A table has fields. So these are the fields, that means the attributes with the following functional dependencies. These are the functional dependencies given to you. Again, you need to find in terms of normalization, this table is in 1NF, 2NF, 3NF or what. So again, you need to find the candidate keys. So F3, F4, F5, F3, F4, F5. That means F1, F2 must be part of every candidate key. Must be part of every candidate key. So let's check whether F1, F2 itself is a candidate key or not. You are getting F1, you are getting F2, finding the closure of F1, F2. Using F1, you can get F3 also. Using F2, you can get F4 also. Using F1, F2, you can get F5 also. So this is your candidate key. Now, do we have any kind of, violation to 2NF? Definitely it is in 1NF. But do we have any violation of 2NF? So if you carefully observe here, F3, F4, F5, all these are your non-prime attributes. All these are your non-prime attributes. Yes or no? So if you carefully see, F1 determines F3. F1 determines F3. Can I say this is a violation of 2NF? Why so? Because proper subset of candidate key. This is your candidate key F1, F2. Proper subset of candidate key determining a non-prime attribute. This is a violation of 2NF. So F1, F2 determines F3. This is the partial dependency that is existing over here. This is the partial dependency. Due to this violation, this partial dependency is there. So it is not in 2NF. It is not in 2NF. If it is not in 2NF, definitely it is only in 1NF. So option A is the correct answer here. Option A is the correct answer over here. Is this clear to all of you? Do you have any doubt? Let's proceed to the last question of today's class, GATE CSE 2022. So let's read the question. In a relational data model, which one of the following statement is true? Option A, a relation with only two attributes is always in BCNF. Yes, this is true. We have seen many times, and many times they have asked this statement in the previous year questions. Option B, if all attributes of a relation are prime attributes, then the relation is in BCNF. No, that is not the case. Right? Because if I want a relation in BCNF, if this is the situation, X determines Y, this has to be a super key. Right? But here it is saying all attributes of a relation are prime attributes. Right? So it may happen that let's say AB determines maybe a C is there and B determines C is also there. Or B determines, C is also there, let's say for example. Then in that case, what will be a problem? Let's say AB is my candidate key. Then in that case, B determines, let's say maybe D. Then in that case, this is not a super key, right? B is not a super key. Even if it is a prime attribute, this is not a super key. So I'm just giving you a simple example. The point is very simple. X has to be a super key. The LHS has to be a super key. Then only we can say the relation is in BCNF, right? So this is false here. Every relation has at least one non-prime attribute. Is this true? No, it is not definitely true, right? We can have zero prime attribute, zero non-prime attribute also. Let's say if you have something like this, if we have a relation, let's say of two attributes, maybe AB, then it may be possible that we have these type of functional dependencies. Now in this case, A is also a super key, B is also a super key. Yes or no? So there is no known prime attribute. So this is also false. This is also false. Right? Here it is saying every relation has at least one non-prime attribute. Here this is a relation, but there is no non-prime attribute. So it is not mandatory that every relation will have at least one non-prime attribute. So this is also false here. BCNF decompositions preserve functional dependencies. No, it may or may not. May or may not. Right? In case of BCNF. So this is also false. It may or may not. So this is also false. Option A is the correct answer over here. That is the only true statement that we have in this question. Is this clear? Do you have any doubt? Anyone? Okay, so that's it. We have solved majority of the questions, and I included a variety of the questions and important questions as well, right? There are few more questions related to normalization that is very easy, and you can also try to solve them. But these statement based questions are really good to solve. So few more questions are remaining that you can try solving yourself also. But the important questions, I would say, that I have already solved in this particular class. I hope you found these sessions, PYQ sessions, really helpful for you. And if you are preparing for GATE DA, then don't forget to check this playlist for AIDA, and I have completed the entire module of reasoning under uncertainty that is there in the subject AI. So this playlist you will find on our channel. You can watch all the lectures from lecture 1 to 9. I have uploaded all those lectures on our YouTube channel of this under this playlist, right? Yes, Abhas, can you please concise the condition for all normal form in one slide? Okay, let me do that. See, if I talk about 1NF in relational model, every relation is in 1NF. Why I'm saying so? Because in relational model, only atomic values are allowed, right? If they explicitly mention that non-atomic values are there, then you can say it is not in 1NF, but by default, it is in 1NF, okay? What about 2NF? For 2NF, if you have something like this, some candidate key, if this kind of partial dependency, not every partial dependency, if this kind of partial dependency is there, then you can say the relation is not in 2NF. The relation is not in 2NF. This is the problem, right? This is the problem. If this kind of partial dependency you find in any relation, you can clearly say it is not in 2NF. Why? This is a partial dependency. What is the violation? Violation will be proper subset of candidate key determining non-prime attribute. This is the violation that we have, and due to this violation, this partial dependency is existing, and that is the reason the relation will not be in 2NF. This is a problem, okay? I hope you are getting this point. Is this clear, Abhas, so far? What about 3NF? What about 3NF? If I have some candidate key determining a non-prime attribute, transitive dependency is there. Transitive dependency is there. If this is the situation, this is also a problem. That means if this is the case, then your relation is not in 3NF. Relation is not in 3NF. So what is the violation? This is the violation for 2NF. Similarly, this is the violation for proper subset of candidate key, transitively determining non-prime attribute. Or in simple ways, how you can check, I'm telling you the other way also, how you can check if I have X determines Y. Either X has to be a super key or Y has to be a prime attribute. If this is the case, then it is in 2N, it is in 3NF. So I'm just giving you a summary of everything. If X is a super key or Y is a prime attribute, then it is in 3NF. But if you have, so ultimately you can say if this is the thing, then you have a problem. This kind of transitive dependency. Understand, not every partial dependency is a problem. Not every transitive dependency is a problem. Which one is a problem? This partial dependency is a problem. If this is the scenario, then it is not in 2NF. Which transitive dependency is a problem? This one is a problem. Is this clear? And what about BCNF? What about BCNF now? In BCNF, it is very simple. If you have X determines Y, X has to be a super key. If this is the case, then it is in BCNF. Otherwise, no. Otherwise, no. Is this clear? Abhas, do you have any other doubt? If you have any other doubt, please let me know in the chat section. Yes, Vipul, since the lecture is over, I have a question related to career. I have a job offer with a decent package of junior data scientist. Should I go for the job and after some years go for MS, or should I see if you have a decent package and already having a junior data scientist role, then I will definitely suggest you to go for job. Okay, because the role that you have is very good, and also you have mentioned that you have a decent package. Then I don't think that you should write GATE. Okay, yes, if you want, you can go for MS abroad. Definitely, if you can afford it, if you are really interested into it, you can go for it. Right? As you are already having a job, that is my suggestion. Then it is my suggestion. Right? Mainly GATE is for those who are interested, who are from tier 3 colleges. They don't have a job, quite a good job offers already in their colleges. Also, they are interested in pursuing MTech from maybe this premier institutes like IIT, ISCs, right? Because they want a handsome package. So for those students, mainly GATE is there, right? But as you are already having a really good offer in hand and role also junior data scientist, so definitely you should not prepare for GATE. Okay, fine. So that is my suggestion. So I hope it is clear, and those who are preparing for GATE, you can definitely watch this complete playlist of reasoning under uncertainty for AI under GATE DA. Okay, for this particular exam. Most welcome, people. So that's it from my side. If you want the PDF of this class, or if you want to connect with us, you can scan this QR code for our Telegram group. This is our Telegram group. Many students have already joined, and this is our QR code for the WhatsApp. And make sure that you like, share, and subscribe to our channel for more such videos, because we are going to complete this entire PYQs sprint. Okay, and the next module we will be starting will be your relational algebra. Okay, we will be solving previous year questions from that particular module. So thank you everyone for joining this. I will see you, and the next class will be on Monday or Tuesday. Okay, so there will be no class on Saturday, Sunday. The next session that I'm going to take on YouTube will be on Monday or Tuesday. Clear? So you will find if you join this Telegram group, you will find all the details there. Otherwise, I will you can also find in our YouTube channel. I will be creating the live link for it in after some time. Okay, so thank you everyone, and keep preparing, keep giving your best. Right, this is the time. This is the most crucial 2 months, I can say, that you have in your hand. So make sure that you utilize it the most, so that you can achieve a very good rank in GATE exam. Okay, and just keep revising, keep practicing, keep giving more and more mock tests, so that, and do make sure that you are analyzing those tests as well. Okay, we'll see you in the next lecture. Till then, take care and bye-bye. Thank you all.